Okay, welcome back everybody. Picking up from where we left off last time, we talked about redox reactions, and now I want to just tell you about stoichiometry problems using solutions. And so really the main unit of measurement that you need to worry about for these particular reactions is molarity or molar. And we talked about this a little bit in class. Molarity is equal to the moles of the solute per liter of solution. So, if you know the moles and you know the liters, then it's pretty easy to find out the molarity. But sometimes you're not given information like that. Like, for example, maybe you're given that you have 40 grams of NaOH, and you're told that you dissolve that in 2 liters of solution, and you're asked to find the molarity. Well, first you have to find the moles. So the gram formula mass for this is 1 mole for every 40 grams. So we would divide 40 by 40 and we would get 1 mole. And then if I wanted to find the molarity, I would divide the 1 mole by the 2 liters, and 1 divided by 2 is 0.5 molar. Likewise, we could try another problem. We could be given like how many liters does it take to make a solution that is 2 molar. And let's say that we decide to use NaCl. And you decide that you're going to put in 116 grams of it. So now, I don't know the liters here, so I would have my 116 grams. The gram formula mass is 58 grams approximately. And so again, if I did this over 1 mole, or 1 mole over 58 grams, I would have that I have 2 moles. Well, the molarity is 2, so if I plug it into my equation, I have my 2 molar equals 2 moles over X liters. You could also do this with factor label method, of course, and so then you would get that you have 1 liter. Sometimes they'll give you milliliters, you have to be careful. This is a graphical interface. It shows if you're going from left to right, you would divide. If you're going from right to left, you would multiply. Most of you honestly wouldn't even look at this graphical interface. I use this with my honors and my regent students sort of as an introduction when I first do it with them. Copy and paste it into this note packet. But a lot of you will do this through, strict dimensional analysis, which I think is actually better. We'll practice some of these molarity questions in class, just finding the molarity. But what if you have, something where you have a type of problem where you have a stoichiometry problem? So let's see how you do with this. Let's say that I were to give you the reaction of zinc and hydrochloric acid forming zinc chloride. Forming zinc chloride and hydrogen gas. And I were to give you a reaction where I said, 35 grams of zinc reacts with 100 milliliters of 3 molar HCl. And I ask you in the problem, how many liters of hydrogen gas are produced at STP. This is something that I really want you to try, so do this problem on your own. Let's see what you come up with. Tomorrow in class we can go over it and talk about the details, share our solutions with each other, see how many liters of HCl that you come up with. So as you can see, this is a straight up stoichiometry problem like what you had on the quiz, except you have a molarity now. And so you have to do something with that molarity. And if you're like, well, I don't know what to do with this, my advice to you is to change it to moles. And let's see why that's the case. If we look at this graphical interface up above here, you need to take that molarity and the volume of the HCl and you need to change it to, let's go up top here, sorry, you need to change it to moles. And the same way, since this is a limiting reagent problem, you need to take your grams of your zinc and also change it to moles. You got to see which one's limiting, and that will allow you to figure out how to get to moles of B. So that's where we're going with this. So try this out, see how you do with it. We'll talk about it tomorrow in class. Now another method that we actually did a titration, but it wasn't an acid-base titration. But this formula here, this is for acid and base titrations. And so what does that look like? Well, you'd be given a problem kind of like this. You'd have your 30 milliliters of 2 molar HCl is used to titrate 45 milliliters of NaOH completely. What is the molarity of the NaOH? And so from last year, you may remember this equation up here that I'll highlight. We can plug in the numbers. You can do this stoichiometrically always, but here I can plug in the numbers for this. The molarity of the acid is 2 molar. The number of H's in the formula is 1. That's for the normality. The volume is 30 milliliters. For the base, the molarity of the base is X. The volume of the base is 45 milliliters. The number of OHs in NaOH is 1. So if I solve for this, I would get X is equal to 60 divided by 45. So when I do this, I get 1.33 as my molarity. So this is an acid-base type problem. Why don't you try one? What if I were to do 50 milliliters of H2SO4 with an unknown concentration, an unknown molarity, is titrated with 25 milliliters of 0.5 molar NaOH. Calculate the molarity of the H2SO4. Now, another type of titration that you may see is one that isn't an acid and base one, and this is what we did for the bleach. This was our bleach lab. And so there we had this titration between the hypochlorite ion, 2 of them, to the thiosulfate ion. And so to do this, you really weren't using MAVA. You were doing straight up stoichiometry. You were finding the moles of one of them, and then, or in this case the S2O3, and then using that to find the moles of the hypochlorite. So in the lab, let's say for example that you used 15 milliliters of 0.1 molar thiosulfate ion. Well, you would convert this to moles. And so when we would do 15 divided by 1,000 times 0.1, we would have 0.0015 moles of S2O3 2-. I then use the ratio, 0.0015 moles of S2O3 times 2 ClO- for every 1 S2O3. This gives me 0.0030 moles of ClO-. Well, if I wanted to find the molarity of the ClO-, I divide it by the volume that I used. I think you were supposed to use 0.025 liters or 25 milliliters So if I divide that by 0.025, I get that the molarity of this was 0.06 molar. In the lab, you had diluted it out 20 times, 5 for 100. So if I times this by 20, I'll get 1.2 molar of the hypochlorite ion. In the lab also, they wanted you to find the percentage, so I could do that as well too. So I could find the percentage by changing this to grams, or changing the moles to grams, and from there I could find the percentage. One last thing in this chapter that I want to talk to you about is dilutions. In dilutions, the equation looks very similar to the titration equation. The idea with the dilution is that the moles stay the same. Remember, molarity is equal to moles over liters. So moles are equal to molarity times liters. So the concentrated moles would be equal to the diluted moles. But what has happened is you've added water. So let's try one of these. Let's say that you had 10 milliliters of an 18 molar sulfuric acid solution, and you want to make this into 6 molar. So the questions that you'll be asked is, 1, what's the final volume? And the second question that you'll be asked is, how much water did you add? So the first one, find the final volume. Well, the molarity of the concentrator was 18. The volume of the concentrator was 10. You want to make this into 6, and you don't know the final concentration. So we have 180 divided by 6, which should give us 30. So that would give us 30 milliliters total. But now, how much water did I add? So 30 milliliters is the answer for the first one. How much water did I add? Well, I started with 10 milliliters. I diluted it out to 30 milliliters. So that means that I added 20 milliliters. This is especially true on the SAT too. They want to always know how much water did you add, and people get it wrong. They put the 30 milliliters, they don't put the 20. Okay, well, this is my video for the solutions. The last part of it, I'm going to post both of these. Please watch this and the Redox video. And then next we're going to move on to gas laws, and hopefully I'll be able to do that fairly, succinctly in, about 2 videos. All right, thanks so much. Bye-bye.